Hello and assalamualaikum everyone. So in this video we're going to move on to another two types of Markovian queuing models involving finite models. Okay, so the first queuing model that we're going to look at is MMCCQ, and then we're going to move on to the finite source queuing model, also known as the machine interference model. Okay, so for MMCCQ, this is basically just a special case of MMCK where you have your K equals to C. Basically, this means that no line is allowed to be formed in the system. Okay, so therefore, any customer that arrive when the system is full will buck. Okay, so this is the transition diagram. Okay, so you can see that up until C, okay, you have your waiting space equals to the number of server. So any customer that arrives, okay, when the system is in state C, okay, will park without even entering. Okay, so from there we will get for MMCCQ, okay, so our arrival rate lambda I is equals to lambda for I equals to 0 up until C minus 1 and 0 when your I is greater equals C. Okay, so for your service rate, we will have equals to I mu when your I equals to 1 up until C and 0 when your I is greater than C. Okay, so the probability that the system is in state I, okay, by using our knowledge from our birth death process, okay, so we will have our pi I equals to lambda to the power of I over I factorial times mu to the power of I pi naught for I equals to 1 until C and 0 when your I is greater than C. Okay, so next we're going to try and obtain the value of pi naught. So for that, let us first denote our R equals to lambda over mu to simplify. So then we will have our pi I equals to R to the power of I over I factorial pi naught for I equals to 1 until C and 0 for I greater than C. Okay, so to determine our pi naught, so we have the summation of I equals to 0 until C, okay, pi I equals to 1, okay, where when you expand, you will get pi naught plus pi 1 plus pi 2 up until pi C equals to 1. Okay, substituting the value of pi 1 until pi C by using this formula. So you will get pi naught plus R over 1 factorial pi naught plus R square over 2 factorial pi naught, okay, up until R to the power of C over C factorial pi naught equals to 1. Okay, so let us factorize pi naught. Okay, so you are left with 1 plus R over 1 factorial plus R square over 2 factorial up until R to the power of C over C factorial equals to 1, okay, which gives you pi naught equals to 1 over 1 plus R over 1 factorial plus R square over factorial over 2 factorial until R to the power of C over C factorial. Okay, so this is basically equals to 1 over the summation of j equals to 0 until C for R to the power of j over j factorial, okay, where your j is equals to 0, 1 up until C. Okay, basically this also can be represented by the number of servers. Okay, so you have to sum up everything to get the value of your pi naught. Okay, So from here we get our steady state distribution. Okay, pi I equals to r to the power of I over I factorial over the summation of j equals to 0 until c r to the power of j over j factorial for your I equals to 1 until c. Okay, and 0 otherwise. Okay, so basically this pi I here is what we call an Erlang first formula. Okay, so when your k is equals to c, okay, when basically it means that the system is full, okay, your pi c here, r over c factorial, okay, over the summation of j equals to 0 until c r to the power of j over j factorial. Okay, this is what we call the Erlang's loss formula. Okay, so pi c is also or can be represented by the fraction of customer who finds the system full and are not allowed to enter. Kind of similar with pi k in our MMCK QE model. Okay, so next we're going to move on to determine, okay, the measure of effectiveness for our MMCCQ. Okay, so first we're going to start with our L, or the number of the customer in the system. So L is equals to the summation of I equals to 0 until C I pi I. Okay, where when you remove the first term when I is equals to 0, so basically you will get the same. Okay, so I equals to 1 until ci pi I. Okay, so you can substitute. Okay, so you will get I r to the power of I over I factorial pi naught. Okay, and then we're going to factorize our r and pi naught. So I equals to 1 until c, so you are left with r to the power of I minus 1 over I minus 1 factorial, because we will cancel out I and the first term of the factorial here. Okay, so you are left with I minus 1 factorial. Okay, and then, okay, rephrasing this, okay, on the right, the summation. So you will get the summation of n equals to 0 up until c minus 1 r to the power of n over n factorial. Okay, so bringing back our pi naught. Okay, so this is actually equals to r times 1 minus pi c, because the only term that is not included here is the term c, so it is actually equals to 1 minus pi c. Okay, so this is the value of our L. Okay, so then next for our W, okay, our W is equals to L over our lambda efficient, since you have a limited waiting space. Okay, so for your lambda efficient, okay, so the summation of I equals to 0 until c minus 1 lambda pi I, okay, which is equals to lambda c minus 1 pi I, so lambda times 1 minus pi c. Okay, similar to MFCKQ. Okay, so since any customer that arrive when the system is full will bulk, okay, so for this particular queuing model, okay, so our LQ is equals to 0, which also means our WQ is equals to 0 because no customer is allowed to form a waiting line. Okay, so now that we have determined all of our measure of effectiveness, okay, for MMCCQ, okay, so we can move on to look at example 4.3. Okay, so in example 4.3, you are given lambda equals to 6, mu equals to 3, c equals to 4. So you need to determine the fraction of customer block for MMCCQ. So basically you need to calculate the fraction of customer block for MM44Q. Okay, so please try that out and we can discuss the solution later during our live session.